Hello, I'm Rhett Davis, and now that Daniel has talked to you about the new analog power modeling capabilities in IEEE 2416, let me go back and talk about the digital power modeling capabilities. Much of this is going to be a repeat from the tutorial that we did at DAC in 2020. We're actually using the same power model here. But what's new is that way we have combined a system level simulation with a real number model Verilog simulation to produce a VCD file to allow us to get dynamic power estimates. That is all very new. If you look at this model, though, and you look at the digital parts of the power, you'll see that it doesn't vary a whole lot. And you might get the wrong impression that there's not very much inside this model. But that's not the case. It's actually fairly complex, and it illustrates how you would create a more detailed power model for a complex piece of IP. So let's go back and look at how we created that model, and then we'll make some more comments as we go. So first of all, if we want to predict dynamic power, we know that that dynamic power is going to vary a lot with the workload that you have running on that IP, but that you can predict it with a number of events, things like transactions over a bus or cache fills in a processor. So if you want to predict the power in that piece of IP, you need to decompose the power energy into a set of different events, and then you need to characterize the switched capacitances for each one of those energy consuming events. And these are what are called the energy contributors in IEEE 2416. And then to predict the power, you just have to simulate to count those events and then estimate the power using this equation here. So to do this for our CPU, we actually used the Rocket Tile processor from UC Berkeley, which is a register transfer level synthesizable model of a complete CPU core with a simple 5-stage pipeline. And we created a capacitance per instruction model for that processor. That's not the most accurate kind of model, but it's enough to illustrate the process of how you would characterize and then simulate this power. We have some more comments later about how you would do something more complex. So that's for the Rocket Tile, and that's most of what I'm going to be talking about here. All of the other blocks in the system used a simple capacitance per cycle model. So let's talk more about how we generated this power model. So to get the most accurate power model, we want to first make sure that we're gathering power information using post-synthesis power analysis of the actual design that we intend to put on our chip. And then we want to gather switching activity from RTL simulations, which will generate VCD files for the switching at the register outputs, and then use activity propagation to all of the gates in the post-synthesis netlist to tell us exactly how much power we're having over a certain window of the VCD file. To generate those simulations, generate those workloads rather, we use the microprobe tool from IBM, which allowed us to create sequences of 1,000 instructions over which we would use to average the power for a large number of instructions. Now, this wasn't entirely straightforward, mainly because we need to make sure that we isolate the kind of event that we're interested in and don't have extra events that don't matter and could throw off the characterization of energy for each one of those events. And when you're doing sequences of instructions, one of the main things that can happen is data dependencies, which cause pipeline hazards and stalls. And if you get those stalls, then you're characterizing the energy for those stalls and not exactly the events that you want. So fortunately, microprobe has a nice feature where you can set the dependency distance for those instructions, and we set it as 5 because we knew that this system had a 5-stage pipeline, and therefore you see that one instruction will be using a register no less than 5 cycles after it was written, and thereby making sure that we don't get any of those pipeline stalls. So see this website if you want to get more ideas about how we generated these workloads. But then from there, it wasn't entirely straightforward, as you'll see next. So as we started running RTL simulations to generate these VCD files, one of the first things we noticed was that there were these periodic interrupts happening every 1,000 cycles or so when the processor would switch from running the user code into running some code for this debug controller that's incorporated into the system. So when that would happen, it would evict a whole bunch of instructions for our instruction cache, generating a bunch of instruction cache misses, as we show down here, as it would, and then a whole bunch of instructions, of course, that had nothing to do with the workload that we were trying to characterize. And then when it switched back into the user workload, we had a whole bunch of evictions again to reload the program that we were trying to simulate. So so we had to do some reverse engineering to figure out the exact switching window in which there were none of these extra events happening. So once we figured out that final window, we knew the start and stop times in the VCD file that we could use for characterization. We also had to go back and actually count the number of instructions that actually executed in that window so that we could get an accurate characterization of the capacitance per instruction. So we repeated this for all 148 different instructions that are supported by the Rocket Tile CPU to get the switched capacitance per instruction, also getting the average number of cycles for each one of those instructions. And with those two pieces of information, we can then build, sorting each one of these instructions from lowest power to highest, get the plot shown here on the left, and then we can multiply that power by the energy, by the time per instruction to get the plot of the energy per instruction as shown here on the right. One of the things you notice from this is that there's a whole lot more variation in the energy than in the power. The power only changes by maybe a factor of 50% from the largest to the smallest, whereas there's a much larger difference in the energy. Most of that is because the number of cycles per instruction changes so much from one to the next. Most of the arithmetic instructions, especially the floating point arithmetic instructions, are really high power, such as this floating point subtract shown down here. Whereas they would actually have relatively less energy because they execute in only one cycle, whereas things like these remainder operations, which take 60 cycles, are dissipating an awful lot of energy as they run over those cycles. So those would end up being the highest energy instructions. Now, simply characterizing the energy per instruction is not going to give you a very accurate power model. So we wanted to add a little bit more accuracy into this by characterizing the energy consumed during certain kinds of stalls. I mean, one of the most basic was the sort of pipeline stall. So what happens during pipeline hazard or a control hazard, which would be like branching to another location. Microprobe actually gave us a branching benchmark that we could use to characterize the amount of time lost when you would do a branch instruction. So that's what we used for characterizing pipeline stalls. To characterize instruction cache energy, we already had a number of instruction cache misses from the benchmarks that we showed before, so we simply analyzed those to see how repeatable they were, and found that in general there were two kinds of numbers of cycles that the system would stall when doing a pipeline fill. Sorry, an instruction cache fill. So we just picked the shorter of those two for simplicity, but if we wanted more complexity, we could probably try to figure out what's the difference between those two events. And then as for the data cache fills, we had to come up with our own special benchmark there, mainly because none of the microprobe generated workloads had any data cache fills at all. So we had to create a special benchmark, which was a simple Gauss sum program, and that we found by increasing the length of the Gauss sum that we were doing, we could force certain numbers of data cache fills, and then subtracting the actual power from the workload using our previous instructions level power model, we were able to get a pretty good idea of how much energy was consumed by a data cache fill event. So here's a sample of the UPM file that's part of this tutorial, illustrating how the rocket tile power model looks in the final code. So you'll see that you've got the different model parameters, the supply voltage shown here. You've got the frequency of the clock, and then you've got the counts for each of those different events, including all the instructions, and then the total number of cycles for all of the events, which is shown here. You also needed to have the capacitance for each event. Those capacitances per event were considered part of the dynamic power expression as shown over here. And then the actual expression for this on state of the processor is simply a long expression that matches the one that we showed here, using all of the different parameters, as you can see in the UPM file. So now let me say a few words about the accuracy of this power model. First of all, if we go back and we actually measure the number of events from the RTL code, and then go back and combine it with the power model that we've just characterized, then you'll see that the cache fills are responsible for an awful lot of the energy in the system. Here we're showing two different versions of the Gauss sum benchmark, one that induces a small number of data cache fills, and another that has a fairly large number of data cache fills. The red part here is the data cache fill energy. You can also see in this green here are the instruction cache fill energy, and you can see these debug interrupts happening occasionally that we talked about before. So this is okay. You'll get a nice detailed idea of the power from running an RTL simulation, but if you just run the instruction set simulator that's coming packaged with this tutorial example, then you're not going to see these data cache events. The simple instruction set simulator does not capture instruction cache or data cache fill events. So if you want to get that kind of accuracy from this kind of power model, you're going to have to replace your instruction set simulator with a more detailed kind of simulator to gather those events. So that's all I was going to say about the rocket tile model. If you want to look at the rest of the model for the digital parts of this tutorial example, you'll see things like the system bus. Basically all the other digital blocks used a simple power model obtained from a vectorless power analysis. So just ran it and without running an RTL simulation, just got the result of how much average power, and then using that put it into these kinds of switched capacitance, so you can still vary the frequency and voltage and see how that changes, but otherwise you're not getting any variation with the amount of activity. If you look at the leakage power, you'll see that, again, it's a simple leakage power for each block. However, we do have this leakage scaling expression, which was derived by Jerry Frankel, who's on the IEEE 2416 team, from the BSIM3 equations. And that just illustrates how you can use a complex expression to see how that leakage power will vary with, with temperature and voltage. So that sums up the power model that you'll see packaged with this tutorial. But let's take some time to talk about how we could make more complex models. In fact, some of the things that we wanted to include in this tutorial, but we couldn't for lack of time. First of all, like we said, instruction level power models aren't really the best. A more typical kind of CPU power model that's used today will have events for large function units. So for example, if you want to look at a typical out of order superscalar processor, such as the boom tile from UC Berkeley, it can be modeled by the popular MacPat model, which for out of order processors, which actually includes 121 different energy consuming events for its different function units. Things like the main pipeline, instruction and data caches, translation look-aside buffers, as well as branch predictors and branch target buffers. So these could easily be converted into UPM. We could go and we could basically take the capacitances per event, translate them into a UPM IEEE 2416 model, and we'd be off predicting power at least at the same level of accuracy as MacPat. But again, in order to do that, you need to have this detailed CPU simulator to count the number of events for each one of those. And that's not necessarily a trivial task, and something that we did not have access to in trying to build the model here, which is one of the main reasons why we didn't include it in this tutorial. But one of the things that we thought about doing that we didn't have time for, which would be much simpler than including a detailed timing simulator, is to just predict the number of events for each one of these function units just based on an instruction trace coming from the instruction set simulator. So just to give a shout out to my student Jiping Wang, who did an investigation of this, where he used a decision tree estimator along with the instruction set simulator for RISC-V, which is called Spike, and then he augmented it with cache predictors and branch prediction simulators, just to see if see how well he could predict the number of other events just from that instruction trace. So then he went and did RTL simulations of Berkeley's boom tile using a whole bunch of different configurations, 100 different configurations for things like the issue width, physical register file, branch predictor sizes, and cache sizes to see how well he could predict the number of events. And then doing that, he essentially took that instruction trace and the number of these different events counted from his simple simulator, and then put through these decision tree estimators to get the event predictions that were needed for MacPat, and then used those to go through and also try to predict the total number of cycles that were going to be consumed by the simulation. Because like we said before, if you can't get the number of cycles correct, then you're going to have very incorrect estimates of the amount of energy for whatever simulation you're doing. So here are some plots that are showing the results of doing this kind of prediction. one of the first things he found that even when he included this extra events into the instruction set simulator, he was still getting about 300 to 2,000 times faster than the detailed timing simulator, which in this case is essentially an RTL simulation of the boom core. So that's pretty fast. Now, in terms of the prediction accuracy, shown over here on the left, we've got prediction including the to the baseline, which is just doing an instruction set simulation with with no other event predictions like cache misses and such, versus the full model, which is actually taking again all of those predictions and seeing how well we can do. The power modeling accuracy was pretty good. We get less than 1% absolute percent error for the power. Energy prediction was not as good, and as you can see here, again in the best case, we're still getting up to 10% error for many of these workloads. Again, why is that? It's really just because of the difficulty of estimating how long it's going to take to run each one of these workloads. Still, it is something. It does give you some kind of prediction, and we could build this into our System C simulation for this tutorial if we wanted to. Just be a little bit more extra effort, but all of the pieces are there. So finally, let's talk about AI workloads. We started this tutorial by saying that we were going to look at AI applications, and hey, where are the AI applications? Well, we really intended to include that into the simulation, so I'm just going to talk a little bit about how we went about it and what we came up with, and how we might be able to add that into a future example. So first we have to start off with some kind of an AI application. We picked as an interesting application that was forward-looking a self-supervised learning application for an embedded image sensor. So you can imagine that if you've got a stacked system on chip with an image sensor and an SoC with it that's going to implement your machine learning algorithm, that it could read out a series of images from this image sensor and then train on those images to figure out what it's seeing. So without having to give it a set of preset classes, it can just it can compare the differences in the images that it sees and develop its own set of classes, which you can then later assign to the different things that it is seeing. One great example of this type of algorithm is the MoCo algorithm from Kai-Ming He at Microsoft Research. So we basically applied the algorithm that he published, which essentially has us running this ResNet 50 convolutional encoding many times as it's trying to train this network to figure out what its different image classes are. So let's look at how we now can investigate that in the context of UPM and IEEE 2416. So I'm going to reference my student Chanli Zhao's dissertation, who worked on this. He basically decided to first look at a systolic array architecture because we were thinking about an embedded system, and systolic arrays tend to execute this kind of workload with much lower power. And so first he had to partition the execution of this MoCo algorithm between some software that would be running on the Rocket core and then the hardware that would be running on the systolic array hardware. And then he so put together a system level simulation for that, and then had to characterize the power of the systolic array. So he did that by taking a high-level synthesis code for different sizes of arrays, synthesizing them and then extrapolating them to different, looking at trends for how the array size was, and then extrapolating those to to figure out how much energy was going to be consumed for other sizes, and then to figure out how long those networks were going to take to execute, use this popular tool ScaleSim for figuring out for certain different convolutional network shapes and sizes how many cycles they would take to run through a systolic array. So these plots here show some of his results. Again, this is all kind of hypothetical, but it shows the kinds of analyses that you can do with UPM. So first of all, in terms of how long it would take, he varied the array size from 16 by 16 to 512 by 512, and saw amusingly that the amount of time it took to actually run through the ResNet 50 network varied from 19 years down to 3 days. So obviously that's not realistic. You're not going to have an embedded application where for every single step, even with the largest array, it takes 3 days to go through and actually calculate that training. So we have a lot of software development that we have to do before we can really come up with a good application to run on this kind of system. Actually going through and looking at the rest of the system, you'll see that he boiled it down to the amount of SRAM energy that was consumed for each one of these evaluations of ResNet 50, as well as the energy for the DRAM axes. And then working that back to figure out how much energy was consumed by the array. So we saw that the DRAM energy was about 10,000 times larger than the SRAM energy, and then the array energy was about 1,000 times larger still than that. So the vast majority of the energy is being consumed in the array. And really, if we want to look at this, we can kind of ignore the SRAM and DRAM energy and just focus on the array energy. If you look at the total sum of the energy here, you'll see that it's wrong. That actually this is an error in Chanli's dissertation that we have to go back and fix. The error is occurring because there was a units problem. He actually forgot and had the array energy in joules, whereas the others were in watt hours. So again, that's a little embarrassing, but it also underscores the reason why we need UPM, that by going through and using spreadsheets, we're prone to errors like this. We really need something that's automatic that can go through and handle these kinds of unit conversions and prevent us from having errors like this. So hopefully this illustrates the digital power model and simulation that's being delivered as part of this example, and also how we would like to expand it in the future, ways that you can take this model and expand it for your own systems. And thanks. Now this concludes my talk. This also concludes the tutorial and this demo system. We've illustrated how IEEE 2416 can aid in the power planning, sequencing, and architecting of a complex mixed signal system that includes power regulators, analog blocks, and complex digital blocks. And we've shown this power calc tool that can predict the amount of power using a UPM model and state information for the system. And then if we want to create a power trace, we can actually take this combined system level real number model system and generate a VCD file and use this scenario generation mechanism to sort of break it down into the instantaneous scenarios that would be needed to predict the power dynamically. That can be used then to explore different power strategies, power saving strategies, and useful when architecting a system. This system that we've put together is simulator agnostic. It doesn't use any specialized code from any vendor, and therefore we can easily distribute it to anyone. It won't necessarily work on every single platform, but we should be able to distribute it, and it should be easily adapted into any vendor's simulation, as long as they can co-simulate System C and System Verilog. And if there's anything that you get from this tutorial, it should be this: no more spreadsheets. We really need to start building our power modeling tools to make use of IEEE 2416 instead of these error-prone techniques that we're so used to. So this concludes the talk. Thanks so much for your attention. And now we'll hand it over to Nagu Danwada, who can make some closing remarks.